Okay, so in a standard linear algebra textbook, tensor products are not actually included. So the new thing about this book, the author introduces tensor products and then we will see the product, which product. Linear algebra is lower because it provides very nice tools. Usually in standard books, these are postponed. In our curriculum, maybe in some elective course they are covered, but not in a mass course. Still the study, and it's the too late. Not too late, but okay, so okay, so here is the definition. Later, I will give more formal definition. This is not a formal definition. This is actually a description of product, tensor, vectors, and so on. Suppose V and W are two vector spaces. So it is over the field K. That one defines any vector space which is called the tensor product of V and W and denoted by this. So what is this object? This is the space of this is the vector space of expressions of the form V1, we call it this tensor product V1 tensor W1, V2 tensor W2, up to Vn tensor Wn for some n positive integer, and V1 up to Vn in V and W1 up to Wn in W. So, tensor product of two vector spaces V and W is the set of objects like this. Okay, and we make this as V1 tensor W1, V2 tensor W2, and so on. it looks like something weird, but we will see that actually it is something you already you are already familiar with. Well, I have to tell you how do we make operations with this, right? So, okay. Further, we postulate the following combinations are equal. So we have this kind of objects, but some of them are or will be considered the same. For example, what do we mean by scalar multiple of a vector of the tensor product? What we will mean is the following. You can multiply the first vector by lambda, right? This is the part, right? This is a vector. Yeah, I can multiply this. And I will also assume that this is the same thing as this one. So I can just take this constant outside of the product or in front of the first vector or second vector. This is my axiom, okay? I assume that this holds true for all V1, so V, W, and you may ask the following: does there, such thing exist? We haven't proved that, but we will prove later that indeed such a thing exists. But right now, I just make the following assumption. Consider this kind of objects, and on this objects, I define some operations. For example, scalar multiplication of this. Whereas V1 plus V2 tensor W. This is the same thing as this one. Actually, we use this the other way around. Whenever I have something like this, meaning that if the second component are the same, then I can just write this like this one. Okay? So as if I am taking to double parentheses, right? V1 times W, V2 times W is equal to V1 plus V2 times W. So it's like usual product, but it is not, of course, usual product. And vice versa, this tensor W1, W2 is the same as V tensor W1 plus V tensor W. So this should hold for all lambda in K, V1, so V1 into V and W, W1, W2 in W. Okay. So that's it. This is the definition of tensor product. We can show that with this operation, actually, this is a vector space. Okay, so postulate. Yani bunları aksiyom olarak kabul ediyoruz. We assume that these rules holds for all lambda V, V1, V2, W, W1, W2. So these rules always true. These actual expressions are the same. This one is the same as this one, is the same as this one. This thing is the same as this one, and this thing is the same as this. So it's like usual product. Okay, this is the distribution norm of product over addition from right and left. And this is a strange gadget. So you can just take this concept over here. Evet.
Hocam biz gayet sanat için yapmıştık böyle V, W diye bir vektör tanımlayı. Burada öyle bir durum geçen böyle bir vektör
Tanımlamadım ben zaten. Yani şöyle, our elements are symbols like this, and this is scalar multiplication, and I didn't tell you what is the addition. Addition is just you add these gadgets. So, what is the vector addition? Okay, now, so this is vector space with following operations. I have to tell you what the addition is. Addition çok kolay. So, let's take two elements. V1, W1, Vn, Wn. This is one element. And then I have another element, right? So my elements of the tensor product are expression like this. I just take two of them. Let's say, since I already used V1, I should use something else, right? Right? So let's say, okay, V1 prime, W1 prime, Vm prime. It doesn't have to have the same number of elements. Tensor Wm prime. So I have to tell you what is the sum of these two. Well, sum of these two is just this thing. You just erase the parentheses. So this is just V1 tensor W1, Vn tensor Wn, plus V1 prime, W1 prime, up to Vm prime, Wm prime. Sum of these two objects is another such object. Tamam mı? What about scalar multiplication? So if I take a scalar, then lambda times V1 tensor W1, and tensor Wn. What is this? Well, you may just take this way. This tensor V1. I just multiply the first vector by lambda. This is my definition. Of course, from our axiom, we see that I can take lambda. I can just take this lambda also over here. So this is the same thing as V1 by Vn. It's the same as this one. Okay, you can define it either way. With these operations, the tensor W becomes a vector space. Of course, one has to prove all the things. For example, what is the inverse of such an element? What is the inverse of this? Inverse element. What is the additive inverse of this? Well, look at this one, minus V tensor W. Now, by our axiom, which one? Second one, this is just V minus V tensor W, right? If I have V1 plus V2 tensor W is V1 tensor W plus V2 tensor W. So this can be written like this, but this is just zero vector times this. Zero times. Evet, bu da yani buna tabii zero diye tarif etmemiz lazım. This is the zero element. Okay, I can just write this zero times actually the right zero vector zero times this, or just zero times the cancel of this, and this is zero. Yani tabii şey söylememiz lazım. Burada zero elemanın ne olduğunu söylemem lazım, değil mi? Onu söylemedik. Kim burada söylüyor mu? Evet, soru diye gelmiş. What is the zero element diye sormuş. Okay. Zero element. Zero element should be this. Zero times W, or so this is the zero element. Of course, I can write this as follows, right? This is just zero times any vector times this. And you see, instead of zero vector, I write zero times any vector. But you know that this is zero times this widget. And this is, I can take this to the second component. So the tensor is zero. So zero element, we may define it this way. It is this one, which is equal to this one. But I have to prove that why this is the zero element, right? Is this really the zero element? Now let's see why it is the zero element. Zero element'e ne yapması lazım? Bir şeye eklediğim zaman onu değiştirmemesi lazım, değil mi? So we must prove this. If this is the zero element, zero tensor W added to any gadget V1 tensor W1, right? Vn tensor Wn should be just this gadget. Why is that? I can do the following. Instead of zero, I can write ne yapabiliriz orada? Ha, aslında şu da var bakın. Not the following. 0 times W, right? This is the same thing as 0 times. Right here, we saw that this is just B tensor 0, right? For any. So for any W and for any. But then this is just 0 times B1, right? I can write anything because 0 times this, B times 0 for any B and W. Okay, so those axioms implies this. But then I can do the following. Instead of this gadget, I can just write this. 0 times W1. So 0 times W1, B1 times W1, B2 times. Oops. W2, Bn times Wn. Well, just look at these two elements. Right? These are both W1, so I can write this 0 plus B1 and tensor W1, B2 tensor W2, Bn tensor Wn. But in this vector space, this is really the 0 element of the vector space. So this is just B1 tensor W1, B2 tensor W2, Bn tensor Wn. So what we have seen is that this element added to this one, and you get the same. Therefore, this acts as if it is the 0 element of our vector space. You can take also to this side and see that the same thing goes. The key thing is that 0 times W is B times 0 for any vectors B and W. Değil mi? Sihir gibi. Okay. Efendim? Nasıl? Evet, evet. Hani inverse ne diye sor. To show that this is a vector space, we have to prove several things. This is an abelian group, so it should have a 0. Well, this is the 0 element. And we should have an identity element, I mean inverse element of right inverse of this is this one because the sum is just 0 element. So in our vector space, 0 element of our vector space, anything like this or anything like this is the 0, and the inverse of minus B tensor W is this digit. Or you can take this, of course, minus sign to the other side, and this is also this one. Ben nasıl cevap vereceğimi bilemiyorum. Yani aksiyomları kullandığı sürece hiçbir sorun yok. Tamam mı? Aksiyomları kullanabilirsin ama onun ya da onlardan ürettiğin bir şey kullanabilirsin ama başka bir şey yapamazsın. Okay, now examples of tensor products. Keep in mind that I haven't actually proved that something like this exists. Well, actually, yeah, we proved, I guess, right? Yeah, I should say the following. Okay, we defined this vector space in a solid way, but later we will see another construction. But that needs quotient space idea. That's why I will a little bit postpone that. Okay, now first example is polynomials. Okay, now as an example, consider this. Let V be the vector space of polynomials in the variable x of degree less than or equal to 2, and W be the space of polynomials of degree again 2, degree less than 2 in the variable y. So B is this kind of objects. So A0 plus A1x plus A2 x squared. A1 A2 A2 so A0 A1 A2 are real one. B is the vector space of all polynomials of degree again at most 2, but this time in the variable y. So B0 y plus B0 sorry plus B1 plus B2 y squared. B0 B1 B2 are real numbers. We may consider the tensor product of these objects. Okay. So I take an element from here, take an element from here, and then write down as a tensor product. For example, an element from this 1 plus x tensor its digit. Using our rules, I can write it this way, right? Consider this as a single element, but this is a sum of 2 elements. So this is just 1 tensor y squared minus 2y plus x tensor y squared minus 2y. Okay. And then this is 1 tensor y squared minus actually it is plus 1 tensor this, right? And then x tensor y squared and then x tensor minus 2y. Okay. So this tensor product can be written like this. So one tensor y squared, and then I can take, since this is just -1 times 2, I can take this -1 outside, right? So it becomes 1. And isterseniz şurada. Here we have -1, but I can just take it outside. So I will get minus. So this becomes plus. And the same thing here. I can take it outside. So what we get is this. 1 tensor y squared, 1 tensor 2y plus x tensor y squared minus x tensor 2y.
Hocam,
Evet.
şimdi biz karışık bir şey için daha da karışık bir şey bu.
Hı hı.
O zaman bu ne yaptık?
Bir soru. Biraz sabır. Now, also note that is it just product of this polynomials, right? I have a polynomial of x and polynomial of y. I can consider both of them as polynomials in the two variable polynomial ring, x and y. So this is an element here, this is an element here. And this is a set of all polynomials in the variables x and y. So these are elements here, and I can just multiply them over there. And what is this? This is just y squared, or 1 times y squared, minus 2 times y, with the y squared, minus 2y, plus x times y squared, minus 2xy. And let's just compare these two expressions, right? What are they? Well, they are basically the same thing, right? They are basically the same thing. Because I can just take this 2 also over here, 2xy. I can just take this 2 over here, 2 times 1. So you just get actually basically the same thing. This means what? You can regard this polynomial algebra as the tensor product of the polynomial algebras Rx and Ry. This shows that you will regard Rxy. So this two variable polynomial ring is a vector space, over R is the tensor product of vector spaces. R X cancel R Y. Yani tek yapacağım şey nedir? Şu garip çarpımı normal çarpımı gibi geçiyor, right? So whenever we have such an expression, just regard the strange looking product as the usual product, and you get this formula. So this gives a way of describing this object as an operation on vector spaces, right? This is just the tensor product of these two vector spaces. So vectors, I mean, tensor product is not something you have maths or that. Sorusu olan bir var. Tamam, söyle.
Bunun application'la ilgili yani bunu nerede kullanıyoruz?
Bunu nerede kullanacağız? İyi soru. Tensor products, and then we will see that alternating tensor products. For example, alternating tensor products are nothing but determinants. Any determinant is actually a tensor product. So, and it's a lot of applications. For example, using tensor products, and there is another version of it, exterior product, you can prove something like this. Let's also explain in the introduction of the book. We can prove the following. Tensor and actually exterior product. Exterior product will be a little bit different than tensor product, but it is basically tensor product. Tensor products provide within explanation for the problem. Very geometric high school fact, but if you try to prove it using analytic geometry or high school geometry, it's not that easy. Here is the fact. Choose only 3 points in the plane, in the space, forming the triangle. So they will have to be on the same line. Okay, they supposedly points like this, and they form a triangle. Okay, it's a so these are just 3 points on the 3 space. I can look at the projection of this triangle on the coordinate planes. For example, in the XY plane, it is a shadow like this, right? Let's call this triangle T1 or T. Let's call this TXY. That is the x-axis, this is the y-axis, this is the z-axis. On the XY, no, YZ plane has also a shadow according to this one. Yani bu kötü bir isim ama anlıyorsunuz YZ. And on this plane, it has also a shadow like this. And let's call this PXZ. So I take the triangle in the space and I look at this projection onto the walls. Yani mesela bu odada alın bir tane üçgen uzayda. Bir geri projeksiyona bakın. Bir tahtaya, bir de şu duvara. 3 tane üçgen elde edeceksiniz. Right? From this triangle, we obtain 3 more triangles. It's projections onto the coordinate planes. The fact is this. I can measure or compute the areas of all these triangles. The areas of these triangles obeys a Pythagorean rule, namely area of T, the big triangle, squared is area of 2xy squared plus area, alanın karesi tabii, üçgenin karesi değil mi? Area of y z squared plus area of x z squared. Did you know this fact? Well, it is a high school stuff, right? Just triangles. You can prove it. It's not difficult. Just take coordinates, look at their projections, and you have to compute areas of 4 triangles. It's not difficult. But using the language of tensor products, it will be just one line. Okay. So such a fact can be written in terms of tensor products and wedge products in a very elegant way. That's why these objects are natural objects. Okay. Although they look a little bit, synthetic objects, right? They are not natural. They don't look like natural, but they are very natural objects. And they have a lot of geometry in them. They are algebraic objects, and we will see that, for example, we can represent linear transformations using tensors, and it will be very convenient when you are making computations. So they are useful in algebra part of linear algebra, but also in the geometric part. So they have geometric meanings, and this is one example. Okay. Try to prove this at home. It's not difficult, but it's not trivial also. And I didn't know this fact, till I read from the introduction. So it is not something, used a lot, but I think it's a very beautiful fact, right? I guess, yeah, we are done. So next time we'll continue.